Assalamualaikum and hi. In this presentation, we will be presenting our case study, Biomass Energy Utilization in Industry. This is our group member. I am Muhammad Hikmah bin Amirul and my friend is Abdul Razik bin Abdul Razak, Daniel Hazil Hakim bin Hanasri, Wais Wafiq bin Hairuddin. Introduction. This is background. With the growing danger of climate change, power plants are shifting from fossil fuel to bioenergy. This study highlights the importance of biomass in industry and energy system, showing how thermodynamic principles like energy balance, efficiency, and heat transfer can improve performance and reduce emission. By analyzing energy flow and loss, the case study demonstrates how biomass support Malaysian effort to cut greenhouse gases while promoting sustainable and ethical industrial practice. Why is sustainability so important? Firstly, biomass rely on organic material. If harvested unsustainably, this resource can be depleted, leading to soil degradation, deforestation, or reduced food security. Secondly, sustainable system aim to maximize conversion efficiency, high energy yield per unit of biomass, while minimizing waste, heat, and emission. This aligns with the principle of reducing entropy generation in energy system. Third, sustainable practice minimize greenhouse gas emission, prevent excessive land use, and reduce water pollution. For example, using crop residue instead of cutting down forests.
So now we will look into the thermodynamic analysis. For our case, it is biomass gasification of banana peel for syngas production. Here, we show the energy balance for the banana peel gasification. So for this study, we uses banana peel as our biomass. 1 kg of banana peel, if fully combusted, can release about somewhere 50,000 kilojoule of chemical energy. From the energy, it is distributed into three parts. First, the syngas. It will produce around 12,000 kilojoule of syngas, energy of syngas, and then 2,000 kilojoule of heat loss, and then 1,000 kilojoule of the production of byproducts such as char, tar, and ash. So from this given value, we calculated the efficiency by dividing the energy of the syngas over the total input. So 12,000 kilojoule over 50,000 kilojoule, and then times it by 100, we will get 80%. 80%. So 80% shows that it is very high efficiency. High efficiency reduces the amount of biomass needed for the industrial energy, making the process more sustainable and cost effective. Now, we will look at major energy losses in the banana peel gasification. First, about 1,000 kilojoules are locked in byproducts such as char, tar, and ash. This happens because not all carbon reacts, leaving a solid residue behind. Second, around 2,000 kilojoules are lost due to irreversibilities and inefficiencies. Real processes are not ideal. Friction, turbulence, incomplete mixing, and chemical reaction inefficiencies consumes energy and reduce their useful work. Lastly, moisture content in banana peel also contribute to the losses. Part of the input energy is used to evaporate instead of producing syngas, lowering the effective heating value compared to the dry biomass. This diagram shows the energy flow diagram for the biomass gasifier based on the first law of thermodynamics for an open system. So the input is the energy for the biomass, and then it will be converted into three outputs. First is the useful energy, the energy of the syngas, the byproduct energy, and then the heat loss to the surrounding. The overall balance is expressed as the energy of the input is equal to the energy of syngas plus the energy of char, which is the energy of byproducts, and then the Q loss. This highlights how energy is conserved and distributed in the process, with syngas as the main useful output, while some energy is inevitably lost or locked in byproducts.
Now, let's talk about sustainability evaluation. Environment impact. Firstly, energy waste. Inefficient combustion or incomplete gasification can lead to wasted energy in the form of unburned carbon or low quality syngas. Other than that, heat losses during conversion reduce overall system efficiency. Secondly, emissions. Biomass generally has lower net CO2 emissions compared to fossil fuels since the carbon release was originally absorbed during plant growth. Resource consumption. Firstly, water and energy inputs. Pre-treatments like drying and grinding consumes energy. Other than that, some processes may require water for cooling or scrubbing, adding to resource demand. Secondly, chemical additive. Catalysts like NiCAO or alkali metal improve syngas quality but require mining, processing, and eventual replacement, which consume resources. There are 5 potential improvements that can be done. First, pre-treatment. Drying to reduce moisture, improving conversion efficiency. Other than that, heat recovery. Capture waste heat from syngas, cooling, or reactor walls to preheat feedstock or generate steam. Furthermore, hybrid system. Couple gasification with solar, thermal, or other renewable input to reduce fossil energy reliance. Next, advanced gas cleaning. Remove tar, particulates, and harmful compounds to lower emissions and improve syngas quality. Lastly, circular use of residues. Char can be used as biochar for soil improvement, closing the carbon loop.
Now we move to proposed engineering solution. For the first solution is implement heat recovery. It relates with first law of thermodynamics. It states that energy can be neither created nor destroyed. It can only change form. The way we implement heat recovery is by employ high efficiency compressor, blowers, and pumps. Another one is insulate reactors and piping to reduce heat losses. For the second solution is optimize process condition. It relates with enthalpy balance. To optimize process condition is to maintain optimal temperature range from 700 to 900 Celsius for complete gasification. Another one is control air-fuel ratio to balance oxidation and reduction reactions. Lastly, apply enthalpy balance. It ensures energy input equals useful energy output. For the final solution is adopt energy efficient equipment. It relates with first law of thermodynamics and second law of thermodynamics. We can apply this by install heat exchanger to recover heat from syngas. Another one is use recovered heat for drying banana peels before gasification. And finally, reduce external fuel demand by recycling thermal energy. Next, we move to ethical and value-based consideration. For environmental responsibility, engineers must minimize emission, energy waste, and ecological damage. Thermodynamics show us that energy degradation is inevitable, but responsible design reduces entropy generation and pollution. For example, using waste heat recovery instead of venting into the environment. For cost versus sustainability trade-off, high efficiency equipment or carbon capture may cost more initially. Investing in efficiency ensures less fuel is consumed long-term. Ethical duty balance affordability with long-term environmental sustainability. Impact on workers, society, and future generation. It offers a safer and cleaner processes protect workers from harmful emissions. Sustainable energy system reduce societal health costs and preserve resources for future generation. Irreversibility today accumulate as burden tomorrow. Lastly, professional ethic of engineers. Engineers are bound by codes or ethics like prioritizing public safety, honesty, and sustainability. Applying thermodynamic principle, responsibility ensure design are not only efficient but also safe and fair. Ethical engineering means choosing solutions that serve society, not just profit.
Conclusion and recommendation. The analysis shows that while chemical energy can be harnessed from biomass justification, the second law of thermodynamics limits the fraction that becomes useful work due to entropy generation, with part of the energy loss as irreversibility, heat, and byproducts. Efficiency improvements such as heat recovery, process optimization, and energy efficient equipment help reduce entropy, sustainability, and recommend solution is an integrated approach that combines these technical strategies with ethical responsibility, balancing costs with long-term benefits, protecting workers' health, and minimizing environmental impact. Together, this finding aligns strongly with SDG 7, SDG 12, and SDG 13, positioning biomass justification as a viable pathway towards sustainability, energy, and societal well-being.